This is going to be an in-depth video on all the information that's necessary to complete your first pre-lab. The lab that we're going to do first is the separation of sodium chloride, NaCl, from silicon dioxide, SiO2, also known as sand. So, the purpose of this experiment is to use the physical properties to separate and calculate the mass of two solids in an unknown sample. So the two solids are going to be salt and sand. They're going to be combined together in an unknown combination. So you're going to have more of one, more of the other. Maybe they might be equal. We're not sure yet. Okay? So in this case, we're going to be testing the solubility of each solid. That's the ability for a substance to dissolve in a solvent. What's a solvent? Well, a solvent is the major portion of a solution. In this class, mostly it's going to be liquids. And in this class, more specifically, the liquid is going to be water. But that's not always the case. Excuse me. Solutes, on the other hand, are the minor portion of a solution. In this case, mostly going to be solids. But that's not always the case. Sometimes your solute can be a liquid. Sometimes it can be a gas. In this case, it's mostly going to be solids. So when we add water, which is our solvent in this case, what's going to happen? Well, the salt that's in the solution will dissolve. The sand will not dissolve, and you're going to form a heterogeneous mixture. More specifically, a heterogeneous mixture with two phases. The first phase is the aqueous phase. The aqueous phase means that it's either water or it's dissolved in water. So in this case, your sodium chloride changes into sodium ions and chloride ions plus water. Those are the three components of the aqueous phase. The solid phase is silicon dioxide. So now you have the salt almost separated from the sand. But how do we get these two phases separate from each other? Well, we remember from class that we can use a filtration system in order to do that. So when we filter out our aqueous phase, we can put that into an Erlenmeyer flask, and we'll have sodium, chloride, and water. Our solid phase will be stuck on the filter paper. This will be the filter paper and the solid phase. So if we took the mass of the filter paper before we started, once it dries over time, we can know the mass of the filter paper and the solid, and we can subtract the filter paper and we'll just be left with the mass of the solid. But we still have to deal with this aqueous phase. So how can we get rid of water but keep the salt? Well, now we're going to start to test the boiling point and the melting point of these two compounds, the water and the salt. As it turns out, water boils at 100 degrees Celsius. Salt boils somewhere in like the thousands of degrees Celsius. So it's a very stable molecule. So we can evaporate the water and we'll be left with just the salt behind. So when we add a heat source to water, what's going to happen? Over time, you're going to see it start to boil, and then the water is going to start to evaporate away. And what are you going to be left with? You're going to be left with salt behind. So if we're able to measure the Erlenmeyer flask before we start the filtration process, once all the water is gone, we'll be left with the mass of the salt and the Erlenmeyer flask. We can subtract those two, and now we'll be able to have the mass of the salt and the mass of the solid phase. Lab complete. Now, why does this process work? This process works because of a process called solvation. This occurs when a solvent dissolves and stabilizes a solute. So when we first start off, we have sodium chloride. Joined together, they're best friends, they hang out, nothing can break them apart. Unless you're a water molecule. So when they are dissolved in water, what actually happens is that your sodium and your chloride separate, and they separate into their constituent ions. Sodium becomes a sodium ion, which is a cation, which is a positive ion. How do we remember that? Cation, a positive ion. Chloride or chlorine turns into chloride, which is a negatively charged atom, which is known as an anion, a negative ion. Now, what's going on with the water? What is so special about water that makes this happen? Well, as it turns out, on a molecular level, it actually looks like this. Interesting. So the water molecules are starting to line up around each ion. The oxygens have something called a lone pair of electrons. They're lining up around the sodium ion. The hydrogen in the water molecules are lining up around the chloride ions, which have valence electrons. Valence electrons, of course, are the outermost electrons in an atom. Next thing that you'll notice, besides the fact that the hydrogens are lining up around these valence electrons in a nice, neat, ordered way, you'll notice something called a hydrogen bond in between adjacent water molecules. So these three things we have to explore because it's all important. So let's start with the way that the water molecules are lining up around the ions. We enter something called a polar compound. A polar compound is a neutral compound with a separation of charges due to uneven sharing of electrons. So covalent compounds share electrons evenly between them. Polar covalent means that they're sharing, but it's uneven sharing. It's like when you're playing PlayStation or Xbox with your older brother and he tends to hog first controller from you. You guys can share, but really it's uneven sharing. So let's take a look at a water molecule and the term electronegativity. So polar covalent compounds, or compounds for short, they come about because of something called electronegativity, chemical property. This is the ability of an atom to attract and hold on to electrons. So as it turns out, oxygen is more electronegative than hydrogen. Therefore, it has more electron density than hydrogen, okay? If something has more electron density, it's going to be more negative. So now you can see oxygen has 8 electrons around it. 4 of them are lone pairs, so 2, 4, and each bond is 2 electrons, so 2, 4, 6, 8 electrons. And the electrons are being more attracted to the oxygen. So therefore, it's going to have more electron density. It's going to be more negative than the hydrogens, which don't really do a good job of attracting electrons. So we get these symbols now. Little cursive looking S guys, right? So what are those? Well, that symbol is a lowercase delta. It means slightly. So oxygen is slightly negative, whereas hydrogen is slightly positive. Oh, now we're getting a separation of charges. So this separation is called, or makes water a polar molecule, polar opposites, polar bears. Just kidding. Anyway, so now we have a negatively charged oxygen, slightly negative, and slightly positive hydrogens. That leads to all the properties that we know about water, most of them anyway. So we show polarity by showing this little arrow with a little plus sign on it. So you see the plus sign here. That positive side points towards the positively end of the molecule. The arrowhead points to the negatively charged portion of the molecule. So now this picture will start to make a lot more sense. So let's redraw it real quick. Okay, so when we first saw the picture, probably didn't make a whole lot of sense. But when we throw polarity on top of that, now it makes a lot more sense, because we have the slightly negative portion of the molecules pointing towards the sodium ion, which is positively charged. We should know that opposites do attract one another. And then on the outside, we have the positively charged. So similar charges repel each other. So naturally, it's going to line up where the oxygen, which is slightly negative, is going to line up towards the sodium ion, which is completely positive. On the other end, we have just the opposite. And this is so cool. We have slightly positively charged hydrogens surrounding a negatively charged chloride ion. So, same thing. We're seeing that polarity. Now look, even in the middle, hydrogen bonds can now be explained, because we have that slightly positively charged and slightly negatively charged portions of the water molecule lining up with one another. That's not by coincidence. There's no coincidences in chemistry. It can all be explained. So, hydrogen bonds. These are intermolecular forces between adjacent polar molecules that contain hydrogen directly bonded to a highly electronegative atom, whether it's nitrogen, oxygen, or fluorine. So let's take a look at some examples of this. Oh, but first, don't confuse hydrogen bonds with chemical bonds. They're not the same thing. Hydrogen bonds is an intermolecular force. Okay, so these are molecules that are side by side with one another. Chemical bonds, on the other hand, are intramolecular forces. That means they're inside the same molecule. That's what holds the molecule together. So bonds, chemical bonds, are one of the strongest chemical forces available. However, hydrogen bonds are the strongest intermolecular force. So make that distinction. So let's take a look at some examples. We have ammonia, NH3. Has 3 hydrogens, 1 nitrogen, and a lone pair of electrons on the nitrogen. Why? Because nitrogen is more electronegative than hydrogen. It can hold on to more electrons. So the polarity is represented here. So now we're going to see that hydrogen bond, because we have the positive and a negative charge lining up on adjacent molecules. Take a look at another example. Hydrogen fluoride, same thing. Hydrogen fluoride, also known as hydrofluoric acid, also displays hydrogen bonding. So we'll look at the polarity. Anytime you see opposite charges lining up, you're going to have hydrogen bonds. So tons of hydrogen bonding going on here. Now let's look at an example of how hydrogen bonding affects the properties of a compound. So we're going to look at ethanol and dimethyl ether. They both have the same chemical formula, where ethanol is C2H6O. Dimethyl ether has the same chemical formula, so that means they have the same molecular mass, but they have different polarities. So ethanol does form hydrogen bonds. You see the polarity vectors, if you will, drawn. So let's look at some of the properties of it. The mass is 46.7 grams per mole. The boiling point is 78.3 degrees Celsius. And the melting point is negative 114.1 degrees Celsius. So that makes this a liquid at room temperature. But dimethyl ether, on the other hand, just switching the molecules around slightly changes the entire properties. Notice that with ethanol, the oxygen is terminal. It's at the end of the molecule. In this case, the oxygen is internal. It's inside the molecule, surrounded by two methyl groups. CH3 is a methyl group. So dimethyl, two methyls, ether is this structure here. Now, in this case, there's no hydrogen bonds. So let's see how that affects the properties. Mass is the same. Boiling point in this case drops all the way down to negative 22.0 degrees Celsius, and the melting point drops down to 138.5 degrees Celsius. And it's a gas at room temperature. So when you look at these two side by side, you notice that hydrogen bonds have a lot to do with that. So substances with molecules that form hydrogen bonds have higher melting points and boiling points. That is a key distinction, because now there's a new force in between the molecules that you have to overcome before boiling can begin. So hydrogen bonds are critical. So let's look at the sort of data analysis that we're going to do in this lab. First portion is percent recovery. After you calculate the mass of your purified salt and your purified sand, I'm going to give you the exact mass of each of those values. So the mass of your pure product, that's what you, yourself, and your lab partners have purified in the lab. The crude product is how much I put in, how much I set up for you. So you're going to take those two values, divide it together, and you're going to multiply it by 100%. So you're going to use percent recovery when no chemical reaction is taking place. So if you're doing chemical reactions and you need to do percent yield, that's a little bit different. Similar, but very different. So in this case, no chemical reactions occurring. So we're going to take, let's say, for example, the mass of our purified sodium chloride is 2.138 grams. The crude mass is 2.274 grams. We're going to divide those two together. The grams drops out because it's in the numerator and denominator. Multiply by 100%, you get 94.019%. Now, quick note about significant figures, okay? Whenever you're multiplying and dividing numbers, your outcome has to match the value of the number that has the least amount of significant figures. So, in this case, our values had 4 significant figures each. Our answer had 5 significant figures. So that means we have to round to make the significant figures match. So in this case, we're going to round it to 94.02% of the sodium chloride was recovered. Okay, fine. By itself, it doesn't mean much. Is this a lot? Is this a little bit? We don't know. So that's what we need to figure out. But before we can do that, we have to talk a little bit about accuracy and precision. So accuracy is a measurement of how close an experimental value is to its true value, or the value taken over the average of many, many experiments. Precision, on the other hand, is a measurement of how close our measurements are to each other. So in common language, you hear these two terms used interchangeably. In science, that's not the case. Accuracy means how close you are to the true value. Precision, how close your repeated experiments are to each other. So this is a common chart that most people use to explain it. We have accuracy in this column, inaccuracy in this column, precision in this row, imprecision in this row. So let's talk about each one individually. This first corner is ideal. You have highly accurate results. Everything's close to the true value, which is the bullseye, and it's highly repeatable, which means it's precise. This is ideal. This is what we strive for. But sometimes we get results like these. They're all close together, but they're not close to the true value. So that means that we're doing our part. We're making precise measurements, but maybe our machine is inaccurate. Maybe we need to come up with a new machine that can give us slightly more accurate values. So usually that's an indication of instrumental error. something you want to address. Now here we have accurate results relatively. Some of them are hitting the mark, some of them are off, but they're not repeatable. They're not grouped together. So this is usually an indication of human error. Something that you're doing is not correct. Maybe you're measuring it differently every time. Maybe you're not following the exact same steps. So if you find that your results are this way, you need to take a look at that. And then we have the worst. We have results that are neither accurate nor precise. It's very difficult to determine the problem of this sort of results, so you need to start from the drawing board, start all over. Okay, now, last slide, let's finish up. The data analysis that we're going to do to understand what the percent recovery truly means is going to be the absolute, relative, and percent error. So first, let's start with absolute error. This is a measurement of how accurate your results are. So the formula for absolute error is experimental value minus the true value. So let's take a look at our example. If our experimental value was 2.138 grams of sodium chloride, the true value was 2.274. You're going to subtract those from one another, and you're going to wind up with negative 0.136 grams of sodium chloride. In chemistry, it's okay to have negative absolute error, okay? Because this is an indication that you lost product when you performed your experiment. And that's to be expected, because not everything is 100% perfect in chemistry. Sometimes we lose product just in our process. Sometimes we have product that's more than what we started with, which that's a little bit harder to explain, but something to be on the lookout for. So once again, absolute error by itself doesn't really mean much. So that's why we got to look at percent error or relative error, both the same. So this compares the absolute error to the true value of the measurement. In other words, how important is our error? So percent error takes the absolute value of the absolute error and it divides it by the true value and multiplies it by 100%. If you need to calculate the relative error, you'll simply not multiply by 100%. But most of the time we talk about percent error in chemistry. Now, that is not helpful to me as a chemist. Because I can't always remember what absolute error is. So because we don't usually report it. So what we usually do for the percent error is the absolute value of the quantity of the experimental value minus the true value, divided by the true value, multiplied by 100%. That's the formula that I use, which is the same thing, just a simple substitution. So let's look at our example. 2.138 grams minus 2.274 grams, take the absolute value, divided by 2.274, multiplied by 100%, and we come up with 5.981%. So in this case, your percent error gives you an indication of how much percentage of your sample you lost in your experiment. If your absolute error is higher, is a positive number, then this tells you how far off percentage-wise you are from the true value. So this is a good number to report. This is the number that I'm going to ask you to report. Now, in most cases, 5 to 10% error is acceptable. In chemistry, we really strive for 5% error. Biology kind of strive for 10% error, but as long as you have an explanation for both, then we can certainly work with that. So that's it. That's the pre-lab, all the information that you need to know. If you have any questions, I'll see you in class.